Hi everyone and welcome to another lecture. So far in our discussion in linear algebra and vector spaces and so on, we only focused on vector spaces with finite dimensions. We took some n and we assume that our n-dimensional vector space is finite. That means the n itself is finite. And today what we're going to do is that we're going to talk about infinite dimensions, and this will be very important in our coming discussions and especially in physics. So the idea for this infinite dimensional vector space will correspond to function space. So what does that mean, right? So let's start with an example. Let's say you are on Earth and you are seeing some vibrating string like this over here, and this is represented by a function that is y equals to f of x, and you have defined this function over this interval 0 to L. Now your friend who's on Mars, he wants to know about this vibrating string as well. So the way to communicate about this string, that is this vibrating string over here, is to decompose the 0 to L interval into, let's say, 30 smaller intervals. And what you do is that, let's say this is from 0 to, I don't know, 0.3 or something. So you are sending some information that when x equals to 0.3, y equals to, let's say, 1. When it's 0.6, it's, let's say, 1.1. And the rule of this game will be not to let know your friend back on Mars about the function itself. So now you are just discretizing the interval and you are taking some values and you are sending it back over here. So these are some array of values. Let's say if you construct it as xy, this will be the first one, let's say 0.31, the second one would be 0.6, 1.1, and so on. And what he will do is that he will take each of these values over here and he will associate, or he will store these values into an array, let's say a column matrix, which is equivalent to a vector, something that we saw in our earlier discussions. So in this way he can construct some basis vectors, for example x1, x2, x3, x4, dot 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 xn. And the more information you send, the smoother his construction of this string will be. And as you can already guess that if you had discretized with n intervals over here, or let's take n plus 1 interval, that is, there are some n plus 1 blocks like this over here. So let's just call it n plus 1 blocks. And ultimately, if you want to identically reconstruct the string from Earth to Mars, you have to put limit n goes to infinity of n plus 1. That is, you have to take really small intervals, and then you have to send them back to Mars to your friend so that that person can construct this whole thing appropriately. So this will become possible only if you have infinite amount of basis vectors. So that's why in infinite dimensions our vectors are functions. So I hope this motivates you on why we are calling the functions as vectors in our infinite dimensions. And let's now, before we finish off, we want to see two small things that will be helpful later. One is orthogonality in infinite dimensions. So from our finite dimensional analysis, finite dimensional vector space, let's say you have a vector space with n dimensions. We knew that if you have a n-dimensional vector space, the basis vectors, they were orthogonal to each other, right? So if you have two basis vectors like this, xi, xj, this would be just delta ij. So this is, let's just put a barrier over here, and I'll write the infinite dimensional counterparts over here. So this is the finite dimension, and this will be our infinite dimensions, right? So this was our orthogonality relation, and the second one was the completeness relation. That is, if you had I is equals to from 1 to n, and you had something like xi, this was just the identity matrix, right? So how does these two things look in infinite dimensions? So that's the question that we are asking. So let's try to answer them. In infinite dimension, our basis vectors, that is, if two things are orthogonal, since we are taking functions to be our vectors over here, so in that sense we are going to represent our bases as like this. Let's say you have one function f, and you can see that I'm putting it inside a bra, and another function g, and if these two are orthogonal to each other, then what will happen is that you should get a delta function, but instead of delta ij, now you will have delta x minus x prime. Here this f is noted is similar to f of x, and g is similar to g of x prime, and this delta is actually a distribution, and sometimes we even call it a delta function, but that's not appropriate. We just call it a delta function, but this is a distribution. And the second thing we want to see is that how does this completeness relationship look, right? So the way to see this completeness relationship is the following. Let's say you have some coordinate basis, that is, this function itself is an abstract thing, this ket, and we'll talk about it later, but today we are just going to skim through these things, and in the later lectures we'll learn more about the details. So f of x can be written as this, and what is happening over here is that you are taking this abstract vector f, the infinite dimensional vector, and you are projecting it into the coordinate basis. So as a result you get this f of x that you are familiar from your calculus courses. So here you can easily find out this completeness relation for infinite dimension. How? Because when there is infinite dimension, instead of n over here, this sum will go to infinity, right? And if you know from calculus that when this goes to infinity, and each of and length of each of these smaller intervals that we discussed over here that they're getting smaller, we should replace this sum with an integral. So let's write this dx over here and just x, and this will be our identity. Notice that this is not a matrix. This is not a matrix. So in case you get confused, just write it as I or 1. And this is the counterpart of the completeness relation. But it's a good practice to always just have this thing, or you can always write it as capital I. So this is an identity. For example, this identity times a function like this, it's just the function itself. And we will see more of this in detail in the later lectures. And thank you.